Okay, in today's lecture, we're going to cover the section 6.4 material, which is on a result known as Green's theorem. Now, before we can state Green's theorem, we need to introduce just a little bit of terminology. So let's suppose that we have a simple closed curve, C, in the plane. So that is a closed curve which does not intersect itself anywhere in between the endpoints. And let's denote by capital D the plane region which is bounded by that curve C. So what we're describing here, let's say that we have some closed curve in the plane, we'll call it C. So its initial point and terminal point are the same. And this curve, since it's a closed curve in the plane, bounds some region, which we're going to call D here, this shaded region that lies inside of this curve. So for such a curve and region, we would say that the positive orientation of this simple closed curve C would refer to a single counterclockwise traversal of this curve. So what we mean by that would be the following orientation. This curve would be traversed in a counterclockwise direction, and that orientation of our curve is said to be the positive orientation. So if we had a similar curve, say some closed curve C, that bounds some plane region D in the plane, we would say that this curve would have a negative orientation if it is traversed in the opposite direction. That is, if it was traversed in a clockwise direction. So this would be a negative orientation. So now that we have the positive orientation of a closed curve defined, we're ready to state the result known as Green's theorem. So here's what Green's theorem says. It says if C is a positively oriented, piecewise smooth, simple closed curve in the plane, and D is the region bounded by that curve, then if we have a vector field in 2 dimensions whose component functions are P and Q, where the component functions P and Q have continuous partial derivatives on some open region which contains D, then the line integral over the closed curve C of our vector field f dot dr, which would be the same as the line integral of p dx plus q with respect to y over that same closed curve, is the same value as the double integral over the region D bounded by that curve of the function partial derivative of q with respect to x minus the partial derivative of p with respect to y with respect to area. So what Green's theorem is doing is giving us a relationship between the line integral of a vector field around a simple closed curve and the double integral over the plane region D, which is bounded by that curve. So Green's theorem gives a relationship between a line integral over a closed plane curve and the double integral over the region bounded by that curve. So for certain line integrals, we can make use of Green's theorem to convert that line integral to a double integral, which might be easier to evaluate than the line integral we're considering. So some examples of this we'll consider throughout this section. And let's look at this first one. We are asked to evaluate the line integral of xy squared with respect to x plus 4x squared y with respect to y over the closed curve C, which is defined to be the positively oriented triangle that has vertices at the origin, 2, 2, and 2, 4. So let's start by visualizing our curve over which we're supposed to be integrating this line integral. So here in the xy plane, we are considering the triangle, which has its vertices at 0, 0, 2, 2, and 2, 4. So we're looking at the following triangle in the xy plane. So we can see, well, this triangle consists of 3 line segments. So if this is positively oriented, we would be traversing that triangle, or those 3 line segments, in a counterclockwise direction. And we see that this curve, this triangle, is not smooth, but it is piecewise smooth. It consists of 3 smooth segments, C1, C2, and C3. So if I were to evaluate this line integral directly, I would have to evaluate the line integral over each of these 3 line segments and take the sum of the values. And to do that, I would have to find a parameterization for each of these line segments and then convert my line integral to an integral in terms of t. So it gets a little tedious here. But if we make use of Green's theorem, we can think about the line integral over this triangle in terms of a double integral over the shaded triangular region D, shown here, and the double integral over that region is not quite as difficult to evaluate here. So let's think about how we need to make use of Green's theorem. So to make use of Green's theorem, we need to determine what are these partial derivatives of q with respect to x and p with respect to y. So let's give ourselves a little notation here. In this problem, p of xy is going to be whatever function we are integrating with respect to x. So in this example, x times y squared, and q of xy is whatever function we are integrating with respect to y. So in this case, 4x squared times y. Now to apply Green's theorem, we need to find these partial derivatives. So here, the partial derivative of p with respect to y is given by 2xy, and the partial derivative of q with respect to x is 8xy. Now notice that these 2 partial derivatives are not the same. So the vector field that has this as its component functions is not conservative. Remember, these are the partial derivatives we consider for the cross partials test. So a little note to the side here, we can say, thus the vector field f, which has these component functions p and q, is not conservative. Now, if this were conservative, well, we know the line integral of a conservative vector field over any closed curve would be 0. But since it's not conservative here, we likely have a non-zero value for this line integral. So to evaluate it, we could make use of Green's theorem. So by Green's theorem, we would have the line integral over the closed curve C of f dot dr, which would be the same as the integral of p dx plus q dy. is given by the double integral over the plane region D bounded by our curve of the difference in the partial derivative of q with respect to x, so that was 8xy, minus the partial derivative of p with respect to y, which was 2xy, integrating with respect to area. So to evaluate this double integral that we're left with over the region D, which is shown as being shaded above, we need to set up an iterated integral. And if we think about this region D as being a type 1 region, we could set up our integral in the following way. So our outer integral with respect to x, well, we see x could range from 0 to 2. And then our inner integral with respect to y would have a lower bound defined by the equation of this line, which is the lower bound for our region. That is the line through the origin in the point 2, 2. So that is the line of slope 1, y-intercept 0, or y equals x. And then the upper bound for our y integral would be the equation of this line, which forms the upper bound for our region D. That is the line through the origin in the point 2, 4. So that is the line of slope 2 through the origin, so y equals 2x. Now combining the terms in our integrand, 8xy minus 2xy, we're left with 6xy, integrating in the order dy dx. So let's see what we have here. Integrating first with respect to y, we're left with the integral from 0 to 2 of 3xy squared, evaluating from x to 2x, and then integrating with respect to x. So we have the integral from 0 to 2 of, when we evaluate at y equals 2x, we have 3x times 4x squared, which gives us 12x cubed, minus when we evaluate at y equals x, we have 3x cubed dx. So we are integrating from 0 to 2 the function 9x cubed dx, which has an antiderivative of 9 over 4x to the fourth, which we're evaluating from 0 to 2. So evaluating at x equals 2, we have 16 times 9 fourths, or 9 times 4, which is 36, minus when we plug in 0 for x, we get 0, so we're left with 36 altogether. So of course, making use of Green's theorem results in this double integral over a relatively simple plane region, this triangular region, and that double integral was much easier to evaluate than trying to evaluate the line integral over each line segment that forms the triangle C1, C2, and C3. So Green's theorem is very useful for evaluating these line integrals over closed curves of vector fields which are not conservative, which bound a plane region that could be integrated easily, making use of a double integral. So let's take a look at another example to illustrate why this theorem is so useful. So in our next example here, we are asked to evaluate the line integral over the closed curve C of x squared plus y squared with respect to x, plus 2xy with respect to y. And the curve C here, we are told consists of the arc of the parabola, y equals x squared from 0, 0 to 2, 4. And then the line segments from 2, 4 to 0, 4, and from 0, 4 back to the origin. So let's sketch our curve here. So in the first quadrant of the xy plane, we are looking at first the arc of the parabola from 0, 0 to 2, 4. So we have this arc opening upward, connecting those 2 points, followed by the line segments from 2, 4 to 0, 4. So 0, 4 is this point. We were looking at the line segment connecting those points. And then followed by the line segment from 0, 4 back to the origin. So that is along the positive y-axis, the line connecting 0, 0 to 0, 4. So if this has the positive orientation, we would be traversing this closed curve, call it C, in 3 segments, C1, C2, and C3. So this curve C is piecewise smooth. So to evaluate this line integral directly, we would have to parameterize each of these segments and evaluate the line integral over each piece and then take the sum. Or we can think about using Green's theorem if we consider the region D bounded by these, or this curve C. We have the following shaded region, and it would be easier to evaluate a double integral over that region instead of evaluating over each curve. Nonetheless, in part A of this example, we are told to evaluate this line integral directly. So to evaluate the line integral using our formula for line integrals, we need to find parametric equations for each of these curves. So let's start by saying parametric equations for the curves are given by C1. So let's think about how to parameterize C1. C1 is the arc of the parabola from 0, 0 to 2, 4. So if we let x equal t, y is defined as x squared, so we would have t squared. And we're moving from 0, 0, which would correspond to t equals 0, to the point 2, 4, which is when t is equal to 2. Now, our second part of this curve, C2, consists of the line segment from 2, 4 to 0, 4. So here, every point on that line segment C2 has a fixed y value of 4. So let's take y as a constant 4. And x is moving from 2 to 0. So we could take for our x parametric equation 2 minus t, where t ranges from 0 to 2. And then for our third segment, C3, for each point on the line segment C3, well, it's on the y-axis, so our x value would be a fixed value of 0. And then y moves from 4 to 0. So one way that we could parameterize y would be to take 4 minus 2 times t, as t ranges from 0 to 2. So in order to evaluate this line integral over the closed curve C of x squared plus y squared with respect to x plus 2xy with respect to y, we would need to integrate this function over each of these segments. That is, we would integrate over the curve C1, this function, for shorthand, let me write it just as f of xy, plus the line integral over C2, plus the line integral over C3. So let's set up the equation, or the integral, to find this first piece, the integral over C1. So C1 was parameterized on the t interval from 0 to 2. The function that we're looking at is the sum of x squared plus y squared. So for C1, x squared would be t squared plus y squared would be t to the fourth. And then we are multiplying by the differential of x. So the differential of x on C1 is just 1 dt. Then we add 2 times x times y. Now x times y on C1 would be t cubed times dy. Now on C1, y is t squared, so dy is going to be 2t dt. Then we add for our curve C2, we're integrating from t equals 0 to 2. We had the sum of x squared plus y squared. Now x was given by 2 minus t, so we have 2 minus t squared, plus y squared. Now on C2, y is equal to 4, so y squared is then 16, times dx. Now x was 2 minus t, so dx is going to be negative 1 dt, plus 2 times x times y. Now x was 2 minus t times y, which is 4, times dy. Now on C2, y is a constant 4, so dy is then 0 dt. So this second piece gives us 0 when we take that product. Then for the last segment over the curve C3, we're integrating from 0 to 2. X squared plus y squared. Now x was 0 on C3, so we just have 4 minus 2t, which was y, quantity squared, times dx. Now on C3, x is 0, so dx is going to be 0 dt. So this term will also be 0. And then we are adding 2 times x times y. But on C3, x is equal to 0. So we have 2 times 0 times 4 minus 2t dy, which would be negative 2 dt on that third line segment. So again, because of that 0 term, this last piece is 0. So let's see what we're left with here. We had the integral from 0 to 2 of t squared plus t to the fourth, and then plus 4 times t to the fourth. So altogether we have 5t to the fourth dt from that first integral over C1. And then for our integral over C2, we are left with, let's see what we have here. So we had a negative dt. So out in front, I can bring the constant of negative 1. I've got the integral from 0 to 2 of, let's see what we have when we expand this term. So expanding this, we would have a t squared minus 4t plus 4 plus 16, so plus 20 dt. So in our last step, we can evaluate this these two integrals and see what we get. So for our first antiderivative, we would have, or let's see, maybe since we're integrating over the same interval, I might prefer to combine some like terms first. So we would have a t squared and then minus t squared integrated over the same interval. So let's see, if we simplify first, we've got the integral from 0 to 2 of my 5t to the fourth, then minus the negative 4t gives me a plus 4t minus 20 dt. And now let's find our antiderivative. So here we would have t to the fifth plus 2t squared minus 20t. We're evaluating from 0 to 2. So plugging in 2 for t, we have 32 plus 8 minus 2 times 20 is 40. And then we subtract what we get when we plug in 0 for t, which would be 0. So here we are left with 40 minus 40, which gives us 0 for the value of this line integral integrated over that curve. So we see here that this was quite tedious. We had to parameterize each of these segments, C1, C2, and C3, and set up a line integral over each segment. And even though some of these segments ended up having line integrals that were 0, it was still pretty tedious to evaluate each of these line integrals. So instead, in part B, if we were to make use of Green's theorem, let's see how this would work. So to use Green's theorem, I'm first going to identify what my functions p and q are. So in this example, p is whatever I'm integrating with respect to x. We have x squared plus y squared. And q is whatever part is being integrated with respect to y, in this case, 2xy. So to use Green's theorem, I need to find the partial derivatives of these functions with respect to x and y. So here the partial derivative of p with respect to y is given by 2y, and the partial derivative of q with respect to x is also 2y. So here we see that since these partial derivatives are equal to each other, we could say that the vector field f that has these component functions p and q is conservative. Running out of space here, is conservative. So we know from the fundamental theorem for line integrals, if we're integrating over a closed curve, that this line integral should give us a 0 value, the same value that we found in part A, or by making use of Green's theorem, as we're told to do in part B of this problem, the line integral of x squared plus y squared dx plus 2xy dy over this closed curve C would be the same as the double integral over the region D of the partial derivative of q with respect to x, which is 2y, minus the partial derivative of p with respect to y, which was also 2y. And we're left with a double integral of 0, which gives us 0, the same value that we found in part A, but for much less work. So this particular example illustrating just how useful Green's theorem can be to save us a lot of work in evaluating these line integrals. So let's look at some other ones that are sort of similar. In this next example, we're asked for the line integral over the closed curve C of x squared y dx, so this function will be our p term, minus 3y squared dy, so this minus 3y squared will be q. And C is the positively oriented circle centered at the origin of radius 2. So let's start by sketching our curve over which we're integrating. So here in the xy plane, we're looking at the circle centered at the origin of radius 2. And we were told it is positively oriented, so traversed in the counterclockwise direction. So it bounds this region D, which here would be the disk of radius 2 centered at the origin. So since this is a line integral over a closed curve, we might first see whether the vector field that has these component functions is conservative, because we know from the fundamental theorem we would have a 0 value immediately. So here, let's start by defining these p and q functions. Again, p is given by x squared times y, and q of xy is defined as negative 3y squared. So the check for a conservative vector field in the plane is the cross partials test. So we would look at the partial derivative of p with respect to y, which here would be x squared, and the partial derivative of q with respect to x is 0 here. So these cross partials are not the same. So the vector field with these component functions is not conservative. A little note here below. This vector field f defined by p and q is not conservative. If we don't know immediately that this line integral over the closed curve is 0, rather than parameterizing this closed curve, making use of polar coordinates, maybe we could more easily evaluate a double integral over this disk. By making use of Green's theorem, we would have the line integral of x squared y dx minus 3y squared dy over this curve C is equivalent to the double integral over the disk bounded by that curve, which we were calling D, of the partial derivative of q with respect to x, which is 0, minus the partial derivative of p with respect to y, that was x squared, integrating with respect to area. So here, we could pull the negative out in front, and we have the double integral over d of x squared dA. Now, to evaluate a double integral, we need to set up an iterated integral over our region. And in this example, because the region D is a disk, we might want to make use of polar coordinates here. So in this example, we could describe our region D as a polar rectangle where our outer interval with respect to theta ranges from 0 to 2 pi. Since we're looking at the full disk, we would have a full 2 pi radian rotation. And the radius could range from 0, those are points at the origin, out to the outer edge of our disk, which was radius 2. So radial coordinate could go from 0 to 2. We have x squared. Now in polar coordinates, x is given by r cosine of theta. So we are squaring that quantity. And then the differential of area, dA, in terms of polar coordinates, is r dr d theta. So let's see what we're left with here. We have a negative integral from 0 to 2 pi, and the integral from 0 to 2. If we expand in group-like terms, we have r cubed times cosine squared of theta, then in the order dr d theta. So again, we can make use of a simplifying trick or technique here. If we look at our inner integral with respect to r, this cosine squared theta term is a constant, and so is d theta. So I could pull the constant cosine squared theta d theta out in front of this integral for r, and I'm left with the negative integral from 0 to 2 pi of cosine squared theta d theta, and then my integral from 0 to 2 of r cubed dr. So really here we just have the product of two different integrals, one with respect to r, one with respect to theta. Now our first one is the integral of cosine squared theta. To integrate cosine squared, we have to use a trig identity. So we would rewrite this as 1 plus cosine of 2 theta all over 2 d theta, and then our integral from 0 to 2 of r cubed dr. So finding the antiderivative for each of these, well, we have our constant of -1 out in front. The antiderivative of 1/2 with respect to theta is theta over 2, and then plus the antiderivative of half of cosine of 2 theta would be 1/4 sine of 2 theta, which we are evaluating from 0 to 2 pi. And then we are multiplying by the antiderivative of r cubed, which would be 1/4 r to the 4th, evaluated from 0 to 2. So evaluating the first antiderivative at theta equals 2 pi, we have the negative of 2 pi over 2, which is pi, plus sine of 4 pi, which is 0. And then we subtract what we get when we plug in 0 for theta, which would be 0 plus sine of 0, or 0. So altogether we just have pi from that first term. And then we're multiplying by, if we evaluate the second antiderivative at r equals 2, we have 2 to the 4th, or 16 over 4, which would be 4, minus when we plug in 0 for r, we get 0. So altogether, we're left with -4 pi. All right. So here, Green's theorem gives us a double integral over some disk, and we see that this double integral is easier to evaluate than if we tried to convert this entire expression to an integral in terms of t by parameterizing the circle of radius 2 that's the outer edge of that disk. Now, in the next part of this section, we'll talk about an application where we might use the opposite direction of Green's theorem. That is, rather than moving from a line integral to a double integral, where we might want to move from a double integral over a bounded plane region to a line integral over the curve that forms the boundary of that region. So one application of this would be in computing the area of some unusually shaped plane region. Now we know that we can use double areas, double integrals, to represent area. So here the area of any plane region D, we can recall, is given by the double integral of 1 with respect to area over that plane region. So that is the area of some region, we recall, is given by the double integral of 1 with respect to area over that region. So if I want to make use of Green's theorem to convert this double integral to a line integral over some curve, then I'm needing to find functions p and q such that the difference in the partial derivative of q with respect to x and the partial derivative of p with respect to y is equal to my integrand, 1 in this case. So there are a few possibilities that we could use here. One easy choice would be to let p be equal to 0 and q be equal to x. So in that case, this difference of our derivatives would give us 1 minus 0. We could take p to be -y and q to be 0, so we would have 0 minus a -1. Or we could take p to be -y over 2 and q to be positive x over 2. So we would have 1/2 minus a -1/2 would give us 1. Several other choices we could use, but these are some standard ones. In which case Green's theorem would give us the following formulas for the area of D. So the area of D, which is this double integral of the constant 1 over this plane region would be found by looking at the line integral of q with respect to y. So in our first choice, where we let q be equal to x, we would have x times dy. In our second choice, where we took p as negative y and q to be 0, we would have negative y, so here a constant negative 1 out in front of the line integral over the curve c of y with respect to x. Or in the last case, where we chose both p and q equal to x over 2 and negative y over 2, well, we would have x over 2 integrated with respect to y minus y over 2 with respect to x. So we can pull out that constant 1/2. So here, what we're doing is if we have some plane region D and we want the area of this region, we could think about the curve C, which forms the outer edge or boundary of that region, and evaluate, instead of the integral over the double integral over D, we could evaluate the line integral around this closed curve. So as an example of this, we are asked to find the area enclosed by the ellipse x squared over a squared plus y squared over b squared equals 1. So let's start by sketching this ellipse. So here in the xy plane, we would have an ellipse where our x-intercepts would be found by setting y equal to 0. So we would have x squared equals a squared, or x is equal to positive or negative a. And our y-intercepts would be found by setting x equal to 0. So we would have y squared is equal to b squared. So our y-intercepts would be positive or negative b. So we have the ellipse, which is passing through those intercepts. So this ellipse we can think of as a curve C, which is traversed in the counterclockwise direction, so it has the positive orientation, and we want the area enclosed by that ellipse. That is the area of this shaded region, which I would call D. So here, to find the area of this region enclosed by the ellipse, D, we could look at the double integral over D of the constant 1 with respect to A. And then I'm going to think about functions P and Q such that the difference in their partial derivatives would be equal to 1. So we said there's a few ways that we could choose those functions P and Q. I'm going to make use of the last choice so that I'm using the following line integral to evaluate that area. So by making use of Green's theorem, we could calculate half of the line integral over the closed curve C, that is the ellipse, of x with respect to y minus y with respect to x. Now, to evaluate the line integral over a curve, we need to parameterize that curve. So for an ellipse, recall that we could set x equal to the x-intercept a times cosine of t, and y equal to the y-intercept, which was b times sine of t, where t ranges from 0 to 2 pi, so that we're tracing out the full ellipse. It's similar to polar coordinates, but where we have different constants a and b, so that we have an ellipse rather than a circle. So now let's set up our integral in terms of t for this line integral. So we had out in front a constant of 1/2. We're integrating over the t interval from 0 to 2 pi. And let's look at our integrand. So the first part was x, which is given by a cosine of t times dy. So if y is equal to b sine of t, then dy is equal to b times cosine of t dt. Then the next part was minus a y. Now y was b sine of t times dx. So if x was equal to a cosine t, then dx is negative a sine t dt. So combining some like terms, here we have 1/2 the integral from 0 to 2 pi of, in the product of these first two terms, we have a times b cosine squared t, and then minus the negative gives us a plus for the product of those terms, a times b sine squared of t, all times dt. So we see that for our integrand, if we factor out the a times b, we're left with cosine squared plus sine squared, which is 1. So this term, which we're integrating, reduces to just the constant a times b. So we have 1/2 the integral from 0 to 2 pi of a times b with respect to t. So that is 1/2 of the constant a times b integrated over an interval of length 2 pi. So the length of our interval we multiply by 2 pi, and we're left with a times b times pi. So the area enclosed by an ellipse that has the given equation is the product of a and b, that is the magnitude of the x and y intercepts, times pi itself. So this is one application where we may use the reverse direction of Green's theorem, where we move from the double integral to a line integral over the curve that bounds that plane region. So let's look at another one. In this next example, we are asked to find the work done by the force field f of xy, whose component functions are going to be p and q here, in moving a particle from the point -2, 0 along the x-axis to 2, 0, and then along the semicircle y equals the square root of 4 minus x squared back to our starting point. So let's sketch out the path of this particle here. So we were told that we're moving along the x-axis from the point -2, 0, along the x-axis to the point 2, 0, and then we are moving along the semicircle, y equals square root of 4 minus x squared, so that is the semicircle, or the upper half circle of radius 2. So we're moving along that back to our starting point. So we're traversing this closed curve C in the counterclockwise direction, so it has the positive orientation. And this is bounding a upper half disk, which I would call D. So if we want to find the work done by this force field and moving the curve along, or moving a particle along that curve, well, the work done is given by the line integral of our vector field f dot dr over the closed curve C. So we could try to parameterize this curve C by thinking of it as two parts. The first part being the line segment from -2, 0 to +2, 0. We could call that C1, followed by the upper half circle of radius 2 back to our starting point. We could call that C2. So there we would need to use polar coordinates to parameterize that curve and evaluate this line integral directly. So it gets a little tedious there, But if we make use of Green's theorem, we could just evaluate over this upper half disk. So let's see what we have here. By Green's theorem, this work done would be the same as the double integral over d of the partial derivative of q with respect to x minus the partial derivative of p with respect to y, integrating with respect to area. So that is the double integral over d of our partial derivative of q with respect to x is 3x squared plus 3y squared. And then we are subtracting the partial derivative of q with p with respect to y. Now p was 7x, so its derivative with respect to y is 0. So what we're left with is the double integral over d of 3 times x squared plus y squared with respect to area. Now, based off the form of this region D, it is a half disk or upper half disk. We might use polar coordinates to evaluate this double integral by setting it up as an iterated integral. So here we have for our outer integral with respect to theta, a theta interval from 0 to pi. Since we were only talking about the upper half disk, we just revolve from theta equals 0, that is the point 20, to negative 20, which would be corresponding to theta equals pi. Then our inner integral with respect to r, well, this was a disk of radius 2, so r could range from 0 to 2. Then the function that we're integrating was 3 times x squared plus y squared, which in polar coordinates is r squared. And then the differential of area, dA, is given by r dr d theta. So we have the integral from 0 to pi and 0 to 2 of 3r cubed dr d theta. And if we're a little clever, we notice this inner integral with respect to r is a constant with respect to theta. So if we were to pull it out in front of our theta integral, we could then evaluate the integral from 0 to pi of d theta, and that gives us just a pi times our integral from 0 to 2 of 3r cubed dr. So save ourselves a little work here. And now we have the constant pi times the antiderivative of this function would be 3/4 r to the 4th power evaluated from 0 to 2. So we're left with pi times, when we evaluate at r equals 2, we have 2 to the 4th or 16 times 3/4 is 12. Minus, when we plug in 0 for r, we have 0. So altogether, we're left with 12 pi for the value of this double integral. So that represents here the work done by this force field in moving the particle along this closed path. So here we see that because these mixed partials, partial of q with respect to x and p with respect to y, were not equal to each other, we did not have a conservative force field. So even though this is a closed path, the work done by that force field is non-zero, since this was not conservative. All right. So in our last example, we are asked a similar problem. We want the work done by the force field, whose component functions here are P and Q. In moving a particle from the origin along the x-axis to the point 1, 0. So let's trace out our curve as we're reading this description here. So So in the xy plane, we were starting at the origin, 0, 0. We're moving along the x-axis to the point 1, 0, and then along the line segment to the point 0, 1. And then back to the origin along the y-axis. So we've got the following curve C, which is a closed curve, and it bounds some triangular region, which we'll call D. So we want the work done by this force field in moving a particle along this indicated triangle. So we know to find work done by a force field in moving a particle along a curve, we evaluate the line integral of that force field over the curve. And here, again, our curve C, since it is a triangle, well, it's not smooth, but it is piecewise smooth. Consists of 3 line segments, C1, C2, and C3. So to evaluate this line integral directly, I would have to parameterize each of those line segments, evaluate the line integral over each piece and take their sum, which we know is a bit tedious. But if we make use of Green's theorem, we could just integrate over this shaded triangular region D, which is much easier here. So let's say by Green's theorem, this work done is the same as the double integral over the plane region D of the partial derivative of q with respect to x minus the partial derivative of p with respect to y, integrated with respect to area. So let's find these partial derivatives. We have the double integral over d of our partial of q with respect to x is y squared minus the partial derivative of p with respect to y is x, integrating with respect to area. So to evaluate the double integral over this triangular region D, we need to set up an iterated integral. So we can think about this region as a type 1 region where our outer integral with respect to x ranges from 0 to 1, and our inner integral with respect to y, well, let's look at the curves that bound y. Our lower value is the x-axis, that is y equals 0, and the upper bound for y is this line, or line segment, passing from 0, 1 to 1, 0. So that would be the line with y-intercept 1, slope -1, or y equals 1 minus x. So that is our upper bound for y in this iterated integral. And the function we were integrating was y squared minus x in the order dy dx. So let's see what we have here. We have now the integral from 0 to 1 of our antiderivative is 1/3 y cubed minus xy, evaluated from y equals 0 to 1 minus x, and then integrated with respect to x. So evaluating at y equals 1 minus x, we have 1/3 of 1 minus x cubed minus x times 1 minus x dx. So to evaluate this, we could do it in a couple of parts. If I split this integral, I would have the integral from 0 to 1 of 1/3 1 minus x cubed dx minus the integral from 0 to 1. If I distribute my x, I would have x minus x squared dx. So let's see what we have here. To evaluate this first antiderivative, I could make use of a substitution. So if I let u be 1 minus x, then du is equal to negative dx. So let's look at what we have. We would have a 1/3 u cubed, and then dx is negative du. So I could bring my negative out in front, I have a du. And then let's change our limits of integration. So here, when x was equal to 0, u is 1 minus x, which would be equal to 1. And when x is equal to 1, u, which is 1 minus x, is then equal to 0. Then we are subtracting the integral from 0 to 1 of x minus x squared dx. So notice for this first antiderivative that the order of our integral we might want to reverse. We were integrating from 1 to 0. We usually want our upper limit of integration to be the larger value. So to reverse the order of those limits of integration, the constant -1 out in front, we would then make a +1. So we have the following. So if we evaluate our antiderivative of this first piece, we have 1/12 u to the 4th from 0 to 1, minus the antiderivative of this second part would be 1/2 x squared minus 1/3 x cubed, evaluated from 0 to 1. So let's see what we're left with here. Plugging in 1 for u, we have 1/12. Minus, when we plug in 0 for u, we have 0. Then we are subtracting. When we plug in 1 for x, we have a 1/2 minus 1/3. Minus, when we plug in 0 for x, we get 0. So altogether, we are left with 1/12 minus 1/2 minus 1/3 would be 1/6 or 2/12. So 1/12 minus 2/12 leaves us with a -1/12 for the work done by that vector field and moving the object along this closed curve. So the fact that this value is negative means that as our object traverses this triangle, the force field acts against it, against the motion of our object, more than in the direction that our object is moving. So in this section, we've got a nice result, Green's theorem, which relates the line integral of a vector field over some closed curve to the double integral over the plane region enclosed by that closed curve. And we see that we would use this theorem if the closed curve C, which is bounding our region, is not smooth, but maybe consists of several piecewise smooth segments. So typically for those types of problems, that's where we're going to make use